Hello and good day. We are from Integrated Design Project Group 2, which include the course Reaction Engineering 1 and Separation Process 2. Our topic is hydrogen production plant via steam methane reforming.
Our group consists of 5 members, which are Alia, Ain, Amrina, Aisa and Zakwan. Let's get started.
The type of reactor that we use for the steam methane reforming SMR reaction is a multi-tubular packed bed reactor PBR. The reason we chose PBR is because PBR is a large combustion furnace to house bundle of parallel long tubes, which means that it can produce a large amount of hydrogen. Second, PBR can keep the catalyst pellets intact, ensuring long catalyst lifespan and reduce costs. Lastly, PBR also is a heterogeneous catalytic reactor, which aligns with SMR reaction, which is also a catalytic reaction. Next, we will move on to the type of catalyst that we use in our reactor. We chose to use a nickel-based catalyst, which is nickel on alumina. The reason we chose nickel on alumina is because first, it has a high intrinsic activity for methane activation, which means that it can produce high yield of hydrogen. Second, it is able to withstand high temperature from 750 to 900 Celsius. Third, it has a high percentage to reduce choke formation. Fourth, it is the most economical for large-scale production compared to other noble metal catalysts. And lastly, it has a mature supply chain which can reduce future risks.
We use 4 key strategies to maximize hydrogen production. First, high temperature. The reaction needs heat. By running at 850 degrees Celsius, we push the reaction to make more hydrogen and also reduce carbon buildup. Second, moderate pressure. The reaction creates more gas molecules. A moderate pressure of 20 bar helps this gas expansion happen, boosting conversion without extra process costs. Third, extra steam. We use a lot of steam, which has the steam to carbon ratio of 3.0. This extra steam stops carbon from forming and clogging the catalyst, keeping it active for longer. And fourth, good reactor design. Our multi-tube reactor spreads heat evenly. This prevents hot spots and keep the reaction stable, which protects the catalyst and ensure high hydrogen output. In short, these 4 choices work together to give us maximum hydrogen efficiently and reliably. Our goal is to design a reactor that produces 3,000 metric tons of hydrogen every year. The main reaction is steam methane reforming. Methane and water vapor react to produce carbon monoxide and hydrogen. This reaction is endothermic, meaning it requires a constant supply of heat. Our solution is a packed bed reactor, specifically a multi-tubular type. Inside the tubes, we use a nickel alumina catalyst. This catalyst is highly active, stable at high temperature, and cost-effective. In simple terms, we mix steam and methane, then pass them through heated tube filled with catalyst. The output is a mixture of hydrogen, carbon monoxide, and some leftover steam and methane. This design efficiently converts natural gas into the hydrogen we need. Let's look at our operating conditions and results. For temperature, we run at 850 degrees Celsius. This high heat drives the reaction forward to produce more hydrogen. For pressure, we use 30 bar. This balances a fast reaction rate with good conversion efficiency. The steam ratio is 3.0. This means we use 3 times more steam than methane, which prevent carbon from forming on our catalyst. Now, for the flow rates, our inputs are 6 to 8 kilomoles per hour of methane and 1884 of steam. The output we're successfully producing is 1695 kilomole per hour of hydrogen along with 565 kilomole of carbon monoxide. These numbers confirm we're hitting our production target.
Now, let's move on to the sizing of the reactor. To calculate the volume of reactor, we follow these 4 steps. The first step is to calculate the fractional volume change and the concentration of all the components. The second step is we assume that the reaction for component A is a first order and we calculate the value of K. Next, we move on to the third step, which is we use the formula FA naught equal to CA naught times with V naught, and we use it to calculate the value of V naught. And lastly, for the fourth step, we use the formula of the volume of PFR, and we assume that the volume of PFR and PBR is the same. Then we use all the data that we have calculated earlier and use it to calculate the final volume, which is then we got the final volume of the reactor is 1.407 meter cube. Then we move on to the yield and selectivity. Yield of a reaction is the ratio of moles of desired product formed to the total moles of reactant consumed. We apply this formula, and after we done the calculation, we got the yield of component D is equal to 3.00. Next is selectivity. Selectivity is the ratio of moles of the desired product formed to the moles of the undesired product formed, which means that higher selectivity in a reaction, it means that most of the reactant will react to form the desired product. Therefore, after we done the calculation, we got the selectivity of our reaction is equal to 3.00.
Right. So the identification of species and concentrations of inherent impurities. We have four types of species, which is the methane CH4, water vapor H2O, carbon monoxide, and carbon dioxide. So the gas stream entering the separator originates from the outlet of the previous packed bed reactor, where the steam methane reforming and subsequent water gas shift reaction occurs. As a result, the stream consists of a mixture of reactant and products including unreacted methane, steam, carbon monoxide, and the desired hydrogen. These species represent both useful product and inherent impurities that must be separated to achieve the required hydrogen purity specification. The molar concentration of each species were determined from the reactor mass balance calculation and equilibrium conversion results performed in the preceding section. The values are summarized in table 3.1, which this consideration provide the basis for downstream unit design, including separation equipment, adsorbent capacity estimation, and purification method selection. So this table illustrates that hydrogen constitute the highest concentration in a mixture, reflecting successful conversion in the reactor stage. However, the presence of CO and unreacted methane remains undesirable due to safety, environmental, and purity constraints. Steam also exists in significant quality and must be removed prior to final purification. This compositional analysis is essential for determining the most suitable separation strategy and ensuring the design system complies with the required hydrogen purity of 99.9% for final product specification.
Hello everyone, my name is Alia, and today we will talk about the final and most important step in our plan, which is cleaning the hydrogen gas to make it 99.9% pure. So we use a system called pressure swing adsorption, or PSA, where this is the most common and trusted method used in industry to make a very pure hydrogen. So here is how it works. We push the dirty gas mixture into a tank filled with a special material, and these impurities get stuck on the material, but the clean hydrogen gas passes right through. So the system has several tanks that work in a cycle, while one tank is cleaning the gas. Another is being cleaned itself to get ready for the next batch. This makes it to have a non-stop flow of pure hydrogen.
Next, I'll be explaining about the selection of adsorbent and adsorption process conditions. Our main goal here is to maximize impurity removal while maintaining a stable hydrogen flow at 99.9% purity. First, let's look at the operating conditions. We maintain a temperature of around 40 degrees Celsius and a pressure of about 20 bar. Why these conditions? It is because higher pressure improves adsorption efficiency and moderate temperature helps capture impurities effectively without compromising hydrogen flow. Next, let's look at the adsorbent layers. We use a multi-layer approach for better performance. The top layer is activated alumina. This layer removes water at the inlet to protect the other adsorbents. Moisture can damage zeolite and reduce adsorption capacity. Next, the middle layer is activated carbon. This layer captures heavier hydrocarbons to prevent pore blockage and maintain efficiency.
Finally, the bottom layer is zeolite 13X. This is the final purification layer. It strongly adsorbs polar gases like carbon monoxide and carbon dioxide to achieve high purity hydrogen. So in summary, this layer design ensures a step-by-step removal of impurities, protects the system and delivers hydrogen at 99.9% purity.
Okay, so topic 3.4, which is the equilibrium isotope of batch adsorption. There are three types of isotope that we need to count of, which is the first is linear isotope, the second is Freundlich isotope, and the last is Langmuir isotope. But we ignore the linear isotope as it is only valid for low pressure and dilute region, which is not suitable for our process. And then to know which one of the isotope is more suitable for our process, we need to plot the data of Q and C and compare the linearity of both graph. Right. So to obtain the value of Q and C of the adsorption of CO2 on zeolite 13X, we obtain the data from past research paper titled Mixed Gas Adsorption. Next, the Q and C plotted using linearized Freundlich isotope equation and linearized Langmuir isotope equation. As you can see in this slide, the plotted graph is both linear for both isotope, as the value of R square for Freundlich isotope is 0.998 and the value of R square for Langmuir isotopes is 0.9908. This indicates that both data plotted is linear, as the value of R square is indistinctively different from each other. So this indicates both isotope can be used for our processes. But according to several other studies, it shows that Langmuir is more suitable as it often fits zeolite CO2 equilibrium data well across the practical pressure range. Next, Langmuir isotope can give more accurate prediction of the equilibrium CO2 concentration in the gas mixture and the zeolite 13X adsorbate, as it has a clear physical basis that matches zeolite behavior. And last but not least, Langmuir parameters are also can be directly usable in adsorption process model and dynamic packed bed simulation.
The secret to the PSA system is the special filtering material inside the tanks. We use 3 different layers, each designed to catch specific dirty particles. So the first layer is made of activated alumina, and its main job is to catch and remove water vapor. And the second layer is zeolite 13X, and it is really good at grabbing carbon dioxide. And the third and final layer, which is activated carbon, it catches the last bit of impurities, which are methane and carbon monoxide. So by using these 3 layers in the right order, we make sure every single impurity is removed efficiently, giving us the 99.9% pure hydrogen that we need. Now, let's talk about how big these cleaning tanks need to be. First, we look at the amount of gas coming from the reactor, which is the total gas flow is over 3,600 kmol per hour. So, to design the tanks, we use some important rules, which is we need to produce 1,695 kmol per hour of clean hydrogen, and the cleaning works at best high pressure 20 bar and warm temperature at 40 Celsius. So, the speed of the gas flowing through the tank is set to 20 meter per second, which is a standard and efficient speed for this process. Based on all of this information, here are the final size for our cleaning tanks. Each tank will have a diameter of 1.4 meter, which is a practical and manageable size. So inside the 3 layer of filtering material will be stacked up. The alumina layer will be 13.5 meter tall, and zeolite layer will be 2 meter, and carbon layer will be 2.8 meter. This makes the total height of the filter material to be 18.25 meter inside each tank. So we also did a check to make sure this height is effective, and the math confirmed that it is perfectly designed to clean the hydrogen truly. So to wrap up, we have designed a cleaning system with tanks that are practical size and will and will reliably produce a large amount of 99.9% pure hydrogen.
So next, let's move on to the regeneration part. Regeneration is the process of restoring the adsorbent bed so it can be reused for adsorption. There are several common methods for bed regeneration, which includes temperature swing, pressure swing, and inert gas purge. First, the temperature swing works by heating the adsorbent to release the adsorbed molecules. This method is best for strongly adsorbed gases like carbon dioxide and VOCs. Next, pressure swing lowers the pressure in the system, which causes the adsorbed molecule to dissolve. This method is energy efficient and allows fast cycles. It's commonly used for oxygen and nitrogen separation, as well as hydrogen purification. Finally, inert gas purge uses an inert gas, such as nitrogen or argon, to displace the adsorbed species. This method is useful when adsorption is weak or when we want to avoid high temperatures. For our system, we use pressure swing adsorption for adsorption and pressure swing desorption for regeneration. We choose PSD because it's faster and uses less energy compared to other methods, making it ideal for efficient operation and shorter cycle times. In summary, PSD aligns perfectly with our adsorption method and ensures efficient regeneration for our system.
In conclusion, our project successfully designs a complete hydrogen plant that meets all objectives. For the reactor, we designed a multi-tubular packed bed system using a nickel catalyst. It operates at 850 degrees Celsius and 30 bar with a steam ratio of 3.0, achieving 90% methane conversion and producing over 1,600 kilomoles of hydrogen per hour. For purification, we designed a pressure swing adsorption system. It uses a layered bed of specialized materials to remove impurities, successfully purifying the hydrogen to 99.9% purity. The key to our success is the seamless integration of the reactor and separator. The output from the reactor feeds directly into the purification unit, creating an efficient and optimized process. This project proves we can design a viable, competitive, and industrial-scale solution for modern hydrogen production. Thank you.